Hi, I'm Kun Sun from George Mason University. This is a joint work with Tsinghua University and Texas A&M University. Jia Hao is the first author. He's a PhD student, but unfortunately he cannot get his visa, so I'm here to give the talk. So this paper is about SDN, software-defined network security, and particularly on this SDN rule installation process. We identify there's one new vulnerability. We call it buffered packet hijacking. And the main idea is actually for this buffered packet, there's an incomplete checking about this buffer ID and the match field. So by using this vulnerability, we see, okay, there's a number of attacks can be developed by misusing this vulnerability. And we also propose some countermeasures to defeat all those attacks. Since all those attacks are new, most existing defense cannot defeat those attacks. The overview, a typical SDN network consists of one centralized controller and a number of switches. So the controllers has a global view of the network. So it can help to make this like a routing decisions for all those switches. And then it will send those commands or those messages to the switch, help them to find the best path. So there's a number of applications maybe are installed on these controllers to help to extend the functionality and capability of the controllers, such as routing, load balance, or security mechanisms. So we use one simple example to show this rule installation process in SDN. So now suppose the host, one host, H1, wants to send a new flow to this another host, H2. So it will first send a first packet to this switch S1. So when S1 receives this packet, he has no idea, okay, where to forward this packet. What's next hop for this packet destined to H2? So it will buffer this first packet into a local buffer area and give a buffer ID. And then it will send a packet in message to the centralized controller. This packet in message contains two informations. One is this buffer ID and also a packet header instead of the entire packet. So after this controller receive this packet in message, and there's a one routing application will calculate one routing path for this new flow. And this one will send back one is a flow mode message to all those switches along the path from H1 to H2. So when S1 receives this flow mode message, it will do two things. First, it will install a rule using this in this flow table, we're using this match field and action. It say, okay, for this destination, for 10.0.0.2, next hop will be S2. Okay, this is like a routing table. So next, it will also using this matched buffer ID. Say, okay, you need to release this buffered packet to its destination. So after this route will be established. And for all the future packets in this flow will be forwarded directly from H1 to S1 to S2 to H2. So in previous work, researchers has identified, okay, what if there's multiple applications receive this packet in and send back multiple flow mode messages? There could be some conflict rules. For example, there's another malicious app. We'll also, after receiving this packet in message, we'll also send another flow mode message. And we can see here in this flow table, it will have two rules. One is say, okay, forward to S2. Another say is job. Okay, there's a conflict. So the attackers typically the goal is, okay, we can send such a flow mode message with high probability, with high priority, so we can override those decisions sent by other applications. So there's a number of works they have that has been proposed solutions to detect those rule conflicts. The idea is we get the match field and actions and detect if there's any conflict. So here is we need to see all flow mode messages. Then we detect if there's any conflicts. However, for the second part, remember we have this buffer ID. How to check this one? There's no research existing work can protect this buffer ID from being misused. So we identify a new vulnerability called this buffered packet hijacking vulnerability. So the idea is quite simple. So here, in normal ways, we see here there's two apps. They have this, the blue one, we send a flow mode message, say, okay, for this buffer ID message should be forwarded to this destination. And for flow mode, for malicious app, they say, okay, for another buffer ID equals to 2, this packet should be dropped. But attackers, malicious app can do one thing. They change this buffer ID from 2 to 1. So if this happened, and when this switch receive this message, this first message with the buffer ID 1 will be dropped. Okay. So the root reason of this vulnerability is there's no checking or consistent checking between this buffer ID and the match field. In other words, when this switch receives this packet flow model, it will only rely on buffer ID to release this buffered packet. So based on this one, we developed 4 attacks. We assume this, the threat model is, okay, we assume this controller switch and the control channels are all secure, and all existing defense mechanisms can be deployed. We assume some applications are untrusted, and also they have the basic permissions to listen this packet in message and install flow mode message. So we will talk about these 4 attacks one by one. This can be attacked different layers, right? Application layer, the control layer, and the data plane layer. And we also verify all those attacks on real SDN testbed with a floodlight controller with some real physical switches. And we generate some background flows used from this using the KDA database. So the first attack is called a cross-app poisoning attack. So in normal way, there's one first packet buffered in this switch 1. And there's a packet in sent to a normal application, app 1. So from this packet in message, app 1 will learn, okay, this H1 is really connecting to the port 1 of the switch 1. So if there's a malicious app X, send another flow mode message, say, okay, the command action is for this buffer ID 1, we do set field, change the source IP to H2's IP address. And then the output is, okay, send this packet to the controller. So when this happens, another packet in message will be sent from the switch to the controller and received by the app Y. And app Y will learn another information, say, OK, to forward for this H2, this host, also connected to the port 1 of the switch 1. So we can see here is an incorrect mapping for the topology of the network. So previously, researchers has developed a number of these cross-app attacks. So for those attacks, their idea is to modify some shared data objects in the control plane. So those attacks can be detected by analyzing this information flow control to detect any policy violation. For our disk cap attack, we use to manipulate this buffered packet in the data plane. So it can escape all this existing defense. So the second attack is for malicious app. This is a packet-in flooding attack. So the idea is, suppose there's one buffered packet here. So attackers send a flow mode message, say, OK, no buffer means send the whole packet instead of only the header. And this group O, 3 action means make 3 copies of this message and send all those separately at the same time to the controller. So we will see the switch will send 3 packet-in message to the SDN controller. So when this happens, if attacker just make the switch copy 24 of those packets, we can see the available bandwidth on the switch will drop to almost 0. And also the CPU is fully busy when this increase to 24. So this is one type of packet-in flooding attack. Previously, this attack is just some, for this attack, the idea is, OK, we can generate some packet which can trigger some match. For those packets, they match no rules in the current flow table. So they will trigger a large number of packet-in messages. So those attacks can be detected or prevented by analyzing the malicious flows or adopting this TCP sync proxy to threshold this number of TCP flooding. For our work, we hijacking this buffered packet. Right? So also, we just want to say, since it generates no malicious flows, so it can escape all existing defense. So third attack is try to bypass the security mechanism, for example, the firewall. So originally, there's one packet for the application Y. In this flow mode, I will say, OK, you need to output this packet, go through the firewall. So if there's another malicious app, it can send another flow message. OK, the flow mode message, say, OK, you instead of go through the firewall, let's go through this S2. So in this way, we can bypass this firewall. So previously, there's also existing some attacks to bypass the security policies. And also, those attacks can be detected to detect if there's any rule conflicts. So for our attack, by manipulating the buffer ID, we don't cause any conflicting rules. The third one is a kind of a DOS attack. So this is a typical TCP 3-way handshake. So the first one will be the T-sync message. So in normal case, when they receive this first packet, TCP sync, this app Y will forward this packet, OK, send in this flow mode, say, OK, you forward it to H2. So if there's a malicious app send a malicious flow mode, say, okay, drop it. Then this host 1 has to send this packet again typically after 1 second. So here the issue is, if you delay this one second, according to one report, is if there's every 100 millisecond delay, this may cost 1% in revenue for Amazon. So this delay doesn't matter. Okay. And all previous defense doesn't study this, consider this attack. So here is one thing for all those attacks based on one condition. Okay, for malicious, those flow mode should arrive the switch before those normal flow mode messages. Right? So how can we guarantee that this happens? So we studied this relationship, the location relationship between applications. So for a number of applications in the controller will be maintained in the processing chains. It could be multiple processing chains. So in one chain, if this packet in message goes through, it will go through all those packet, these apps in turn, one by one. So if there's only one such chain, so we can say if this malicious app is sitting before those target apps, then we can guarantee its flow mode message can arrive to the switch before this flow mode from this target app. So what if there's multiple chains? And also here, if your malicious app are sitting in a different chains on those ones. So now the condition is, what if still the same thing is like the flow mode from malicious app will, if it can arrive on the switch before those applications, then our attack can succeed. So to verify this, we do some experiments, real experiment. We just have these 2 processing chains, 1 and 2. And we have this number of applications, and we have this 5, in each chain, we have 5 locations to insert this malicious app. So we show that if there's for the intra-chain hijacking probability will be either 0 or 100%. If it's before it succeeds. If after it, then fail. And if there's in the different chains, then we see the location will matter, and also the probability, successful probability will decrease according to the location will be near to the tail of the chain. But here one thing is, it's not only for the successful rate, it's not only related to the location of the packet, it's also related to the processing delay for each application. Some application will spend much more time to process some packet. So we also have this one theoretical analysis of this probability, and the result is matched well to our physical experiments. So the detail can be found in our paper. So for defense, there's 2 options. One is, okay, we perform this consistent checking on the switch, or we can perform it on the centralized controller. So for the problem to deploy it on the switch is there are so many switches from different vendors. You cannot just make sure to force all those vendors, okay, you fix those problems. So we choose to fix these attacks on the controller, centralized controller, by installing one layer of this checking. Okay, the idea is we not only checking the buffer ID, but we also match both ID and also the match field, say if there's any inconsistencies. So if after we deploy our this defense called this call checker, we see if there's a 1 in a packet in message, if this packet header is 1 value, and also if for this flow mode packet, they have the same buffer ID, but this match field has a different IP address, we will see, okay, there is a conflict. We can detect the attack. So the conclusion, in this work, we identify a new vulnerability on this SDN rule installation process. And based on this vulnerability, we developed 4 buffered packet hijacking attacks. And also we developed 1 countermeasure, which are lightweight and application transparent countermeasure. OK, that's it. Thank you.